All right. Well, thanks for coming, everyone. I think it's great that we're finally able to do this joint meeting to have some cross discussion between the desk dark matter streams group and the stars Milky Way and local volume science collaboration. So today we have a couple exciting talks on extragalactic streams from Sarah and Aaron. And then if we have any extra time, I think we'll hear some updates from the stars Milky Way local volume collaboration and maybe have a little bit of time for discussion about possible collaborations between the two groups, but we'll definitely do more of these meetings if we don't get to all of that today. So I think we can just get started. So first, we're going to hear from Sarah Pearson. So Sarah, if you'd like to share your screen, you can go ahead.
Yes, hello everyone. Just gonna share. Do you just see the actual slide now?
Yes,
Yes.
with a little message in front of it.
Ooh. There we go.
Yeah, looks good.
Does that look good? Okay. All right. Well, I was asked to talk a little bit about the work my group in Copenhagen is doing on extragalactic streams and also streams in general, and what that might teach us about dark matter now that we'll have really large statistical samples of streams coming up. Okay, so my group is interested in using streams in three different ways to probe dark matter halos and also to test dark matter subhalos and the subhalo mass function. And then I'm also interested in using stellar streams for accretion histories. And today I'll focus mostly on the big bubble here, dark matter halos, but I'll also touch a little bit on the subhalos. Okay, so we've actually known about extragalactic streams for many decades. However, the work on what we can actually use extragalactic streams for, theoretically, and for dark matter specifically, has kind of just been taking off the last couple of years. So all of this is very exciting right now because we are going from knowing about hundreds of extragalactic streams to now probably knowing tens of thousands, if not a lot more. So most of those will be streams from dwarf galaxies that are accreted onto other systems. That could be dwarf hosts and also Milky Way or more massive hosts. But we might also detect globular cluster streams around other galaxies than our own Milky Way. So I probably don't need to tell this group too much detail about this, but one of the exciting things that streams are useful for is that they can actually probe the extent of dark matter clumping, which varies across different predictions from different dark matter particle candidates. So here we're seeing traditional cold dark matter, where you actually have a lot of these low mass subhalos that specifically globular cluster streams are sensitive to. But beyond that, there's also a lot of work showing that a dark matter halo should actually be triaxial and have certain degrees of flattenings that evolve depending on their host mass, but also depending on their redshifts. So if we could actually get at probing dark matter halo shapes across different redshifts from extragalactic streams, with all of these many streams we're about to get, that would be very exciting too. Then we have predictions for the radial distribution of dark matter within halos, where SIDM famously can produce cores, and traditionally lambda CDM is known to produce more cuspy profiles. However, there is a lot of debate in these fields now, since baryons can also make things more cored, and since SIDM can also produce cusps. So it's a bit more messy than maybe we were hoping. But the point here is to say that stellar streams are actually sensitive to both the dark matter subhalo mass function and to the dark matter halo properties, which in turn could hopefully tell us something about the nature of dark matter. So my goal with this first project I'm going to show you by Jake Neibauer and I is to try to use the on-sky morphology of all of these thousands of streams that we're about to detect to learn about dark matter halos specifically. So just to illustrate from our recent paper a few months ago at this point, what we're trying to do. So here on the left, you're seeing an NFW density profile with galactocentric radius, where gamma here is setting the inner density slope and beta is the outer density slope. So this is a traditional NFW profile. So in this paper, we make a mock stream, or we simulate a stream with certain initial conditions. And here, X and C should just be projected sky plane, but now converted into the galactocentric frame. So this is assuming you're seeing the morphology of the stream on sky, and then knowing the distance to the host and converting into the galactocentric system. But all you actually know here is the progenitor on sky position and then the morphology of the stream. So first we set out to test, is there actually something to learn about the radial profile from these streams? So here I'm now showing instead a chord profile with gamma of 0.2, and this is the same initial conditions for the stream, but as you can see, it changes in its morphology. Then we can also instead have a cuspy central part with gamma equals 1, but now a shallower outer density slope of beta equals 2, and again, the stream looks different. So we can then look at this all together and see that even by eye, you can actually see the curvature of the stream changing, which isn't so odd because when you do a different mass profile, you're redistributing the mass within the system. But also you could see that the radii of the turning points of the streams and the actual time scale in which, so they're all integrated for 500 megayears, but they reach different orbital phases in this time due to the interplay between the azimuthal and radial periods. So all of this is quite exciting because it's telling that hopefully some information in the morphology alone. So Jake and I set out to write a sampler that we called Extreme that uses his stream sculpture code, which both leverages JAX, but also is GPU accelerated. So in the paper, we now move from that stream I was showing you before, that's the inner stream, and also this one that's in the outer halo, the outer stream. So we do something crude here. We just mock observe the streams by assuming we would only see the densest parts of the stream. You can do this in a lot more fancy way if you'd like. And then we present each of these mock streams as kernel density with kernel density estimator. And then these red dots that you're seeing would actually be the input to this sampler that we're writing, where the goal is to test which initial conditions, both for the progenitor, orbit and mass, and also halo, mass, and profile, which are the unknowns we would like to know, would actually be able to reproduce the morphology of these streams. So that's kind of the test we're setting up. So we're essentially running thousands of different model streams and asking which type of initial conditions would ever reproduce the morphology you're seeing on sky, which is of course then what we would hope to do for observations as well. So instead of showing you big corner plots, I'll just tell you that the sampler actually is able to recover the true orbital parameters, progenitor mass, and also halo set limits on the halo's radial profile, which is exciting. So here's just showing the best fit, which shows that the actual stream that the sampler finds as the best fit looks a lot like this gray input data that you're getting behind. And then we have the streams that are consistent within our sampler, also shows up as nice matches to the input data. But then the sampler, the region that our sampler is ruling out, saying this is not a good fit, also doesn't look like a good fit. So I think even more powerfully than just saying what is the true dark matter halo potential here, we're finding a region of allowed solutions and then we're able to rule out solutions that don't work. So I think that's very exciting from the on-sky morphology of the stream alone. And I forgot to say the only thing we fix here is the progenitor position, but that could also essentially be relaxed. It would just be more expensive. Okay, so just to show you more clearly how we stitch together the radial profile is that we have then limits on the gamma and beta ranges that are allowed. And from that, from each of the two different streams, we get two different constraints. And let me just first say the dark shaded region here is the prior range, and then the white line is the true NFW, which is a static potential in which we evolved those inner and outer streams as our truth case, which would be the observation. So in reality, you would not know the shape of this white line, but the point is then that the streams actually constrain the radial density profile, and that different streams located in different parts of the halo would be sensitive to slightly different aspects of this profile. So if you're seeing multiple streams, you're probably able to actually stitch together the radial profile of the galaxy. So this is exciting for a test of coarse cusp if we could find streams in dwarf galaxies, for example, but it's also exciting because we could start getting at the outer density slopes of halos, which would in turn tell us about accretion histories and the filamentary environment. So this was all focused on the radial profile, but in the beginning of this talk, I also showed you that halo shapes should vary, and we could actually easily change the code to also test for flattening and triaxiality. Okay, so moving on a little bit to another project we're now working on with Jake as well, is kind of getting at how wrong we are by this assumption of a static halo. Because my whole project I explained now was assuming we see a stream in an observation and then try to assess the present day mass profile of the halo. But we all know that dark matter halos actually evolve in time. They can even have their center of mass shifted around. You could have an asymmetric halo at some point from an accretion event. And here I'm showing the Magellanic Stream, which we famously know have a big impact on some of the Milky Way type streams. So in that sense, we know we're actually wrong in assuming redshift 0 static potential. But the question for these extragalactic systems where we really won't have the kinematics to always know, is there a massive satellite? How is it moving? We could hopefully sometimes see it and avoid those systems, but we won't fully know the truth. So here, I'm now setting out to answer how wrong we are by assuming a static halo. So to do that, in the paper I'm working on now, Adrian Thaub from UPenn has made this beautiful mock observation of one of the fire M12M system, where this is actually now for Euclid. I wish we had one for LSST. We don't have that right now, but definitely in the works. And here you're seeing mock observation of M12M at the distance of Sen A, and for what Euclid would see at different magnitude cuts. So in a simulation, we're lucky enough that we actually have the stream particles identified. So here we're seeing 3 different streams: the S-shaped stream, massive stream, and curlicue stream. And then the whole problem here becomes, if we assume that fire M12M redshift 0 snapshot is our static truth for the whole potential, which we know is wrong, what does our sampler then tell us? Do we actually still learn anything about the truth, or will we then be too biased by the fact that the system has changed too much and there's nothing to be learned by just assuming a redshift 0 static snapshot? Okay, so throughout the rest of this talk, I will discuss this S-shaped stream. Called going off, which a lot of familiar with, which I'm in 2022. Okay, so in the simulation world, we luckily know the truth, so we have something to compare against. So here you're just in white seeing the matter radial profile from the particle data, and sky position of the progenitor, here of the S-shaped stream, and use the morphology as our input. Okay, so before we really get started with applying extreme, there's a simpler test we could do, which is saying, here we know we can pick out each of the particles that belong to this S-shaped stream. Then we also know, as I just showed you, the redshift 0 density profile of the dark matter halo and what the baryons are doing. So we actually also have access to the 6D information of this stream. So we actually know how it's moving. This is just an animation from Adrian, but we know how it's moving because we have access to the true parameters. So as a first test, we actually set out to just see how does these particle spray simulations that are the rapid simulations we're using to generate streams, also within extreme, how does that actually do by under the assumption of this redshift 0 fit to the dark matter halo. So here's what we get. Doesn't look great, actually. It doesn't really look like the stream on the left. But there's that one big assumption that we know is wrong in all of these particle spray simulations if you use them for dwarf galaxy streams, and that's the fact that in particle spray simulations, you are stripping stars at every single time step, which we know isn't the case for dwarf galaxy streams. So we could, similar to what I did in 2022, we can apply something called a tidal radius condition, where we use the fact that we know that stellar streams only actually strip stars, or progenitors only strip stars, if your extent of your progenitor is similar to the tidal radius of your system. So you won't actually lose stars unless the tidal field is strong enough for you to lose stars. So we can actually very simply add this into our extreme framework, and then turn that to stars only showing at pericenter, which we know is more realistic. So this is no fitting at all, but now, as you can see, just by that simple change, the stream looks a lot like the stream. This is all surprising, right? That how does it look so similar when we know we're assuming respond to previously stripped material at a previous center, the angle of those aren't actually exactly matched, right? And that's because the halo has evolved in time. But the most recent stripped material, can you see my cursor actually, Nora? Yeah, so the most recently stripped material here won't be as affected by the change in the halo. And the exciting part about that is in reality, the most recently stripped material will also be the densest part, so often what we'll see. So of course, this isn't a perfect scenario because we won't always know, but at least it's encouraging that it seems like the stream is behaving somewhat well under these simplified assumptions. Okay, so just applying extreme to this now, we can represent this stream with the kernel density estimator and run our code with all the same assumptions as before. And now, instead of showing you the best fit, I'm actually going to show you a subset of the corner plot, where now you're seeing in the y-axis the halo mass, and sorry, in the lower left panel, and then the progenitor mass. And our sampler actually finds a strong constraint on both. And the exciting part, since this is simulations, is that we actually know the truths. And I think this is really cool that we actually, from this sampler, even assuming redshift 0 snapshot, no evolving halo, we actually can get at the true halo mass and progenitor mass. And also, I'm not showing you all the parameters, but actually also the orbit and limits on the radial profile. So on that note, on the radial profile, similar to what I showed for Jake's and I paper, you can then again show our prior range that we sample within. Here's the truth for M12M. And here's the limits that we get from this S-shaped stream. So if you look at the top left plot, you can see that there's a somewhat flat distribution. So we're not really gaining any information on the inner flattening, which isn't so strange, since this part is kind of stream is sitting in the somewhat outer halo. But there is an upper limit on beta, which then in turn constrains the outer density slope of M12M. So I won't go into the other two streams, but I will just say from this alone that it's exciting that it seems as though there is hope to use galactic streams to actually learn about the halo shape. And then Nora, is it okay to spend 4 minutes or how are we?
Yeah, that's fine.
Okay. So summary of this is I'm hopeful that all the exciting streams we're about to find will be useful to learn about dark matter halos. So since this is LSST related, I also just wanted to touch on a paper I had out last year with Anna Bonata and Yingtian Chen and Oleg Gnaden, where we tried to ask how many streams we might be missing in the Milky Way, and also ask which of those would be observable. So there's a lot of assumptions that go into this, some of which have already been updated recently by other papers. And I won't go into too much detail other than to say that this is built on the Chen and Knedin hierarchical model of globular cluster formation, where they take illustrious TNG, have some criteria for globular cluster formation based on major merger times for certain halos. They select Milky Way type systems that also have a GSE type merger and a certain range of circular velocities to match the Milky Way. And they apply some globular cluster sampling technique and assign globular clusters to young stars in the illustrious TNG 50. And then they have tidal disruption based on the tidal field of that entire galaxy. So there are a lot of assumptions that go into this, but what is really cool about the work is that they're able to, in an iterative process and post-processing, reproduce the kinematics, metallicities, and spatial distribution of the observed Milky Way globular clusters. So they actually match really well what the clusters in the Milky Way are doing. So what Anna and I did was we tried to make an extension, a self-consistent extension of the model to actually look at all the debris in their hierarchical model, which was said to be fully disrupted. So here we're not tracking globulars that have some tidal disruption. We're just saying what were their fully disrupted systems. And then from their catalogs, we have the time of formation, we have the positions, the masses, the time of dissolution, and the age and metallicities of all of these globular clusters. And of course, many assumptions go into this, but at least it's somewhat self-consistent. So I'm not going to go too much into detail, but just flash that some of the exciting results is that it seems as if the Milky Way would have about 9,000 fully disrupted systems that we wouldn't be able to see at present day, but that there are about 1,800 streams that might be observable. And this is a little optimistic. I'll get into that in a second. But first of all, I'll say that a lot of this fully disrupted debris are things that just come too close into the center. Then if you split up the surviving streams, you can actually see that most of the accreted streams are the ones that we would find in the outskirts of the halo. So sorry, I didn't even say this is number of objects versus galactocentric radius for the Milky Way. And you can compare this to this number might be slightly outdated, but about 70 observed fully disrupted globular cluster streams in the Milky Way, and see that we might actually be missing some of these very exciting streams in the outskirts. And the reason I think those are exciting is because they would probably be less susceptible to interactions with the galactic bars, spiral arms, molecular clouds that could also lead to gaps. So they might be a cleaner test to look for subhalos. Then there's all these streams that are in the inner part of the galaxy. Mind you, we did not have a galactic bar in this work, so some of these would have been dispersed and phase mixed due to that. But there are probably streams to be discovered in the inner region of the Milky Way as well, and people have already started to find those, for example, with Via Machina cited here. So I think that's exciting that we might have a lot more streams to discover. So my very last point is just we did a crude estimate of what LSST would be able to see for these streams in the outskirts in particular. So what we did was just we said, since we had access to the cluster age, metallicity, initial mass, we actually had all the information we needed to produce these isochrones. And then we actually just did a very simple thing of saying they're probably observable if the main sequence turnoff in LSST is more than 1 magnitude above the LSST limits for resolved stars. So sorry, what I meant, if the actual main sequence turnoff of that cluster we're looking at, or stream we're looking at. And this is how some of the Milky Way streams have been detected as well. So if you now look at this distance indicator here, that's now galactocentric distance. So now you're seeing all the streams that we generated that are beyond 3 kpc of the center, and now beyond 5 kpc, beyond 7, beyond 10, beyond 15. And just a fun comparison, the current streams that we know in Gal streams are only about 20, and we're predicting at the order of 100 streams. So I think that is exciting. And as I mentioned briefly, there are already updates that do this type of analysis with more realistic tidal stripping and also in evolving halos. But I do think this is all very exciting when we're thinking about dark matter subhalo searches for stellar streams. And I think that was all I wanted to say. I'll just leave the summary and take any questions that you might have. Thank you.
Yeah, hi. Thank you for that. And that was wonderful. I love the tie-in at the end to local Milky Way streams. Just a very quick comment. Of course, within local volume, I noticed that we're talking about dwarf galaxy streams. You know, within local volume, of course, we'll have resolved stellar populations and probably even some kinematic constraints from long time frame proper motion studies.
Yes. Okay. Sorry. Was that a comment? It was just a comment, or what? What did you have a question?
Yeah. That was just a comment about looking at streams around dwarf galaxies.
Yes. And
Yeah.
actually, there is also a lot of extra information. If you have kinematics or tip of the red giant branch distance indicators, that's great for all of this modeling because it really limits the parameter space and makes everything a lot faster. So that's really exciting that we could do a lot more with a local volume.
Great. And thank you again.
Thanks.
Okay.
Hi, Sarah. That was really fun. I have a couple of questions, one of which I've asked you before, so maybe I'll miss that one. The one I was thinking about was when you showed, if you skip back to the slide where you're showing where those predicted globular cluster streams are,
Like,
the one as a function of distance. I
yeah.
thought it was like, I agree with you. The stuff that's really exciting is 100 kpc or even beyond 100 kpc. So I'm wondering, like, you're thinking a handful of streams out to the virial radius, even globular cluster ones? Do you-
Sorry, I'm having Zoom issues where I can't see my own cursor.
Because I can see it going out to 100 and just beyond, but it would be great to get all the way out to 300.
Yes. Well, so all of this is with a big caveat, right? That what Oleg and Bill, as he goes by also, are trying to reproduce is the current globular cluster population. So there is the big caveat that they're actually assuming in their work that every cluster beyond 10 to the 4 has been discovered. So I think there's probably going to be updates to that type of forecast as well. So I'm not sure I would trust this like hard limit of 100. We might go further. But it would be accreted. I say that and it says that on the slide, but I didn't really mention it. I think this would all be from accreted dwarfs that then came in with a cluster that then started stripping after accretion.
And in any case, if we had the accreted dwarfs, we'd have the accreted streams from the accreted dwarfs anyway, their own streams too. So,
Yes. Yeah.
okay, super. Thank you. Lovely talk.
Thank you. Yeah, Richard?
Yeah, thank you, Sarah. Yeah, I mean, this is pretty interesting. I was wondering about when you're fitting the like say the fire time dependence, but fixing it to redshift 0, and you do a pretty good job of recovering parameters, like getting constraints on parameters. So I guess, yeah, the question is, like, do you get any extra benefit by including any sort of time dependence, or is it fine to just do this like ubiquitously for all halos?
Yes. So first of all, it's not by chance that I showed you the most simple stream because the other ones are a bit more messy, right? So it does get harder once you have multiple wraps. And I think there is a way we could actually, or we have already tried that, include simple prescription for time growth of the halo based on how we know this halo is actually growing. And that does then change the angle of these outer wraps that I was showing. I guess I can go back to it. Or I can show you all 3 streams. I think I have those here. So that would change this like outer little wrap angle, right? So there's a way that if you include time dependence, you could actually match all things probably better. But once you start thinking about real observations, I just think it's going to be really hard, right? Because you don't know the growth of that specific halo. But it's not ruled out that you couldn't do some kind of average based on what we know from cosmological sims in observations as well.
Okay, great. Thank you.
Akshara?
Hi, Sarah. Thanks for the talk. I was wondering, actually, a bit derived from Catherine's question, but I was wondering, we do know sort of what are the more massive mergers that the Milky Way has experienced to some extent. So can we put some limits based on like the mass of those halos and the number of global clusters you would expect from that, and kind of put some sort of an expectation of the number of global cluster streams that we would
So that's
see
kind
based
of
on that
what,
creation?
yes,
Yeah.
that's kind of what they're doing because they're trying to find in TNG things that have something like a GSE merger. And then remember, they also match the metallicity and radial distribution of the clusters. So that is what they're trying to do. But of course, it's not going to be perfectly the Milky Way's history. But I think it's a really good approach in terms of this iterative process. That's kind of the best you could do at this point. But then there's also the how do you actually seed, because you can't do globular cluster formation in these cosmological simulations. So at some point you also have to like tag the star particles that you say are going to be your globular clusters. So that's why it's a iterative process until they match the Milky Way. So they are trying to use that information, but it's not going to be a one-to-one map.
Okay. Yeah.
Yeah.
Thanks.
All right, I think we should move on to the next talk, but thank you, Sarah. This was great.
Thanks. So
I
my cursor
will-
is gone, so you might have to kick me out to make me stop share. Oh, now I think, there we go.
Oh,
Okay, I found it.
good, great.
Yeah.
I'll pass off facilitation for the rest of the meeting to Peregrine then.
Yes, hi. So onward to the next talk that you have on deck, right?
Go ahead and get set up. Thank you.
Okay.
Share that. All right, how's that? Is it working?
Looks good.
All right, thanks everyone for the opportunity to present here. Thanks to Sarah for setting the stage for a lot of exciting things with extragalactic streams. I'm going to be talking primarily about the observational side, and here are some of the mostly students that are leading and supporting this work. So I guess I don't need to motivate too much why to study extragalactic streams, and there's a lot of important work being done on Milky Way accretion history and things we can measure about the Milky Way we'll never be able to do for any other galaxy. But at the same time, there are certain limitations. For example, the stochastic histories of galaxies, and so it's important to uh, observe as many galaxies as we can to get statistics, correlations with other parameters of accretion histories, and also the dark matter profiles. As we heard from Sarah, there are various ideas on how to test for different models of dark matter using different aspects of streams and diffuse stellar halos for that matter. So moving on to the observational goals, here's an example of a simulated galaxy. It's this spiral galaxy here from the New Horizons simulation. This tiny little box at the center is this visible stellar disk, and then this is down to some low surface brightness, the complicated stellar halo full of substructure. And the prediction here is that as you go from sort of legacy survey depth to LSST depth, all of a sudden you're going from finding about 5% of this material to 50% roughly. And I'll come back to this, but I seem to be hearing about 30 magnitudes surface brightness is kind of the magic number we want to get to really start making major strides in this area. So here's sort of the state of the art at the moment for on various ongoing projects to look at halo substructures with various ground-based imaging surveys, and one of them being Decal's legacy survey. David Martinez Delgado collaborators. These are some of their examples. You can go to R-band depth of about 28.5 surface brightness. This is one of these areas which is kind of notorious for like, how do you define the depth of an image? I mean, I've sort of noticed that even if a formal depth is given, that the streams are not necessarily found at that depth. They can be brighter, the ones that are actually detected. So I'm kind of keeping an eye on that, trying to understand that. The expected depth from the full 10-year LSST survey is expected to be at least a magnitude deeper, possibly two, depending on whose different estimates have been done to have varied by about a magnitude in depth a prediction for what this is going to be like. So it was one of these things that we'll find out as we get the data. Now to give a little example of the sort of science you can do with this. This is again a very bright shell. This is something we have on the archive recently of a nearby spiral galaxy with this shell accretion event. You might be able to see little extra plumes, much fainter on the left and the right there, which one of our team has modeled accretion event to reproduce this morphology, and as a fairly massive dwarf accretion event. This dwarf also has an apparent nuclear star cluster in the process of disruption. So we've gone out and got spectrum of that, modeled the star formation history, and it's kind of this nice match between the starburst that you get about 1 gigayear ago compared to the simulated paracentric passage at the same time point. And so this combination of methods can give you a powerful reconstruction of what's happened with an accretion event. Now moving on to diffuse stellar halos, this is sort of where you're not seeing the direct substructure, and typically you're mapping out an integrated surface light profile. This is, for example, from the Dragonfly survey of mapping out a nearby edge-on disk galaxies, and this becomes another powerful test of theory. This is kind of a standard plot that's been used over the years of accreted stellar mass fraction against the mass of the galaxy. And there's some predictions up here, and then there's some observations that kind of go below there. And there's been some claims of tension with standard theory for years. And I think that much more systematic, surveys are still needed to test these results. So now moving on to Rubin, you've all seen the first look imaging of the Virgo cluster, really spectacular. This is from one of the Rubin PR slides, and I do this zoom in on this area. And just to note that I think even looking at this, I'm somewhat familiar with this giant elliptical galaxy up there. As far as I know, these specific substructures have not been seen, or this bridge to this other galaxy, the tidal features are not been mentioned in the literature. So already just by looking at these images, you can see new features. And I know the actual science grade observations are not going to be available for a while, but there's already things we could start doing with them semi-qualitatively, semi-quantitatively. Comparing this, for example, get an idea of what the depth is of the image, compared here to this famous Case Western Reserve Burrell Schmidt survey from years ago, Chris Mijos and collaborators of image of different parts of the Virgo cluster. This is the south part. And there we have some quantitative idea of what the surface brightness is, and we can compare to what we see in Rubin. And, it's difficult to do very quantitatively. We can say we could at least get to 29 magnitudes in the B band. Of course, the hope is that we're going to get significantly deeper than that. It's a little hard to tell so far how deep it's really getting. Just another example of what you can do. So some of these smaller aperture telescopes end up having, for example, large PSFs. So masking out objects ends up removing a lot of your features. But with Rubin, you're going to have less of a problem with that. And you can see that masking out, subtracting this giant elliptical galaxy, you can see a lot of these, the same spectacular features has been seen before, but in a lot more detail, new features. This disrupting dwarf galaxy, which was known, but it's got a much longer tidal plume than I think was recognized. And there's a bunch of other new features there that when we get the science grade images, hopefully be analyzed in detail and interpreted. And this is just an example of, let's say, starting to model the diffuse stellar halo of these galaxies. I've done a surface photometry on it to get the ellipticity profile with radius, and it matches up very well with previous ground-based imaging. Again, the depth is going to be hard to tell so far what depth we're going to get to. So now moving on from the first look imaging to the DP1, like the actual science grade images, and there's a big difference here in what's been done with the sky. So some really great efforts have been made with the first look imaging to do sky subtraction that preserves large scale surface brightness features. And hopefully we'll hear more about that in the future. Hopefully it'll be applied to some of the forthcoming data. That's not been done for this DP1 data. Here's an example of a nearby giant galaxy. You can see this classic donut hole because of sky subtraction problems. So there have been appeals from the community to perhaps put out two versions of COADs, one of them that's optimized more for this sort of thing. The Galaxy collaboration mentioned that in our request for DP2. And I guess we're keeping an eye on that to see what happens if, how much we're going to be able to do this low surface brightness, large scale work. Now, another interesting result from the first look data, this is a paper which hopefully will be out in the archive very soon, is you could, just by visual inspection, there was a new feature that came out around this nearby spiral galaxy, a giant stellar plume from a accreted dwarf galaxy. And we published in a little more details, but this one, this galaxy is known to be a starburst galaxy, and I think that perhaps this is the impact that of a satellite provoked that starburst, which is not recognized until now. Now, again, looking at a little more comparison of what extra depth Rubin provides, it's hard to be quantitative so far, but qualitatively, you can see there's a huge difference between decals and Rubin. And once you knew this stream was here, you can see it in decals, much more strongly detected in Rubin, much greater detail. And that means that this is relatively high surface brightness. It means you'll be able to get fainter ones once you get the science grade imaging. And this is an example of what you might be able to do with lower surface brightness. You might be able to see around the periphery of this galaxy, there's something going on with the inner halo, some irregularities, asymmetries. Some of that I suspect is still a sky subtraction problem, but some of it we've been able to check with other imaging sources. It looks like it's probably real. So there's some hints of the much lower surface brightness science you'll be able to start doing with stellar halos and outer disks of galaxies. Now, like I said, in DP1, there's a sky subtraction problem on large scales, but if you limit yourself to smaller spatial scales, it should be good enough. And so One of my students has been focusing on doing this on relatively distant galaxies, say redshift of 0.1, where the sky subtraction would be fine, and inventorying some of the halo substructures. This is an example that hopefully will be coming out soon of a stream along the minor axis of this disk galaxy. Again, somewhat bright, and we're hoping to see fainter ones. We don't have an idea yet how deep we can really go with the stack. This is supposed to be 10-year equivalent depth, so hopefully we'll be able to find even fainter features than this. But this is just a preview of some of the other galaxies in the same image, a variety of halo streams and substructures seen. Now, there's a lot of importance in combining Rubin complementing with other types of observations for synergy. One of the things is to combine with space-based imaging like Roman and Euclid. This is an example, again, from that same deep field from Rubin of the same objects seen now in Euclid. And you can see the same tidal features. They're seen in more detail in Euclid, probably slightly lower surface brightness level as well. So when you look at what's complementary about these, I think it's not clear yet if Rubin's going to go deeper than these space observatories or not. We'll see, but it definitely provides the bluer bands that those don't have, which is important for various reasons. Those provide the near infrared in space. And so combining these, it helps with object selection, also helps with stellar populations, going from the blue, from the U band in particular, all the way up to the near infrared. And the other thing that Euclid and Rubin will provide is fine details of the structures, also finding star clusters, nuclear clusters, and globular clusters that are associated with these substructures. So speaking of which, so I'm going to talk a little bit about globular clusters as halo tracers. And as a reminder, this is the M31 on the left, Milky Way mock observation on the right of the globular cluster systems with some indication of metallicities here. And just a reminder that if you didn't know anything else about the halos, if you just looked at the globular cluster systems, you would already know that M31 had a more active accretion history just from the globular clusters. And that can be linked to details about the stellar halos to kind of get a full picture of the assembly history. So in the extragalactic observations, then you can not only use those to map out low surface brightness features spatially, but also then you can go after globular clusters as spectroscopic targets. And so this is something our group did pilot work with this over the years with a few interesting systems. It's called the Umbrella Galaxy, where we used globular clusters and planetary nebulae as kinematic tracers to kind of map out the orbit of this accreted stream, and then sort of made a simple model of the stream to get the 3D structure and try to get the orbital timescales, things like that. Also been able, in a Virgo cluster, been able to use globular clusters to map out a stream there between these two galaxies. And you don't even have to see the stream spatially. Like for example, in M87, we use position, velocity, phase space with globular clusters, and we're able to find a shell there that was accretion event not previously known. And you can go beyond that and call it chemical dynamical tracers, not just kinematics, but use the stellar populations of the globular clusters, give you things like a possible age of accretion event or the metallicity, mass of the progenitor. So, okay, now moving on to Rubin, there's been some interesting, predictions and work shown to kind of simulate what we expect to detect in the LSST of millions of globular clusters, depending on the distance we want. And to really fully study them, one of the great challenges in this field has always been identifying globular clusters versus other things, background galaxies, foreground stars. And so by the synergy of the U band from Rubin and near infrared bands from the space and the resolution from the space, you can then identify those globular clusters much more accurately. This is a nice depth chart to show that Euclid and Rubin for a typical globular cluster, the LSST depth and the Euclid wide field survey depth are pretty well matched. And this is another example showing how this method of going from the U band out to the near infrared can really be powerful in separating out different classes of objects from stars to globular clusters to background galaxies. So our group is doing some work on this at the moment with the Rubin data, but don't have anything to show yet, so stay tuned on that. And I know a lot of other people in the community are working on that as well. Yes, I do have one to show. Well, it's not really any results yet. This is an example of a nearby spiral in DP1, and it's also in Euclid. And so you can kind of see the example of the synergy here. At the top, you can see that the colors that you can measure with Rubin will help identify the globulars, and as well as the high resolution at the bottom from Euclid will also help. But the challenges here, if you want to do this in an automated way and search for globular clusters, is when you get near large galaxies, just like this, there's sky subtraction problems, there's also automated cataloging problems. The deep blending algorithms get thwarted, and they're not optimized for this. So at the moment, this sort of work has to be done manually, of going in and doing our own galaxy subtraction photometry, etc. But if there were ways to improve those catalogs near bright objects, that would be helpful for automated searches. So if I have time, how much more time do I have?
We're down to the last 9 minutes, Aaron. So 4 minutes.
Yeah. Okay, thanks. All right, I'll talk at least briefly about dwarf galaxies, and particularly this interesting class of low surface brightness galaxies called ultra diffuse galaxies. Perhaps most of you have heard of these. They were recognized about 10 years ago as being unusually large for a dwarf galaxy, about the same scale length as a giant spiral like the Milky Way. A lot of work on trying to understand them, both theoretically and observationally. It seems like they're a mixed bag of objects, some of them as just inflated normal dwarfs, while others seem to be an interesting class of galaxies we call failed galaxies. They're telling us something interesting about galaxy formation and globular cluster formation, which are associated with these galaxies. They also have interesting range of dark matter, from basically zero dark matter to two overmassive halos, which were useful for constraining galaxy formation theory, also have been used to test different models for dark matter. But despite the 10 years of being worked on, the surveys are pretty limited and biased. So this is where LSST comes in, of giving us a much more comprehensive inventory of these things and new things that we didn't know about. These are still at about, say, 25 magnitudes surface brightness typically. And so if we go down to 30 magnitudes, there's already some work heard about that people are starting to see more and more galaxies emerging as you go to those lower surface brightness. But here's an example of something you can actually do with the existing Rubin data. This is a UDG candidate as seen in Legacy, and in Rubin it's much deeper. So this is not a matter of finding it. This is a relatively bright UDG, but you can actually analyze its properties in much more detail: stellar populations, internal structure. You can start to see signs of globular clusters in this object, a clumping from star formation. This was also in Euclid. Again, the complementary near infrared helps with stellar populations, and you can see the globular clusters more clearly. We can give a rough guess of the distance to about 50 megaparsec to this object, and it just tells us that this is just the tip of the iceberg. We expect LSST will be a UDG discovery machine. We've done some stellar population modeling of this galaxy from the far ultraviolet to the near infrared. You can be able to constrain its metallicity, its age, its star formation history, and kind of some possible interpretation about this being a dwarf that was expanded from feedback. So I'll stop there with the dwarfs and just go to summary about with LSB Science and LSST. We expect to be getting much more comprehensive census of tidal features around galaxies. Also, there's diffuse stellar halos. Start doing much more work with globular clusters as halo tracers, and much more extensive inventories of low surface brightness dwarfs like UDGs. And so some of the challenges here and opportunities are we're not sure yet what the real depth is going to be in practice of LSST. And we know that good sky subtraction is going to be crucial for a lot of this. And it remains to be seen what's going to be done there, what can be done there. Also pointing out the other observatories that are very powerful, providing synergies, both the space-based and needing spectroscopic follow-up to get a full picture of these systems.
Great, awesome. So very, very quickly. So two things. I just wanted to remind people that I've shared Akshara's presentation on low metallicity streams. So please check that out. And a question for you, Aaron. In the low surface brightness world, how are you disentangling the emission from interstellar cirrus as a foreground?
Yeah, well, that is becoming more and more of a challenge as you get to lower surface brightness. Most of these things I'm showing have not been at low surface brightness enough to worry about that, but I know there are various efforts to model the foreground using color-based methods, for example. That is going to be a challenge, especially if you get to areas where lower galactic latitudes.
Okay, great. And of course, cirrus is also ubiquitous, right? Even at high latitudes.
Mhm.
Right. We've got time for a couple quick questions. Yes, Catherine, please.
Hi, Aaron. I thought the M61 image was really striking. So I'm just wondering, it's so collimated and off center. I'm wondering if I wanted to see further. Like, isn't there a little bit more further out, or do you really run out of stream when you get far out from the galaxy?
Well, yes, I'd be very keen to have a theorist kind of help interpret this. Yeah, here it is. Oh, I don't have a nice zoom in here, but you can see this plume on the right, and there's some interesting
Yeah.
substructure there with
Yeah.
it looks like a secondary shell. We're not seeing anything farther out. We're interested in like a counter shell or stream on the left side. We're not seeing that. So I mean, it seems like it's something very early stages of disruption if you're only seeing this small path of the part of the orbit.
Yeah. Okay, so this extremely brilliant theorist agrees with what you just said.
Oh, okay, thanks.
Okay. All right. Anybody else? Going once, going twice. Well, thank you all. And back to Nora. Anything you want to add before we close this out?
I don't think so. Yeah, thanks
Yeah,
for the great
and
talks.
definitely we should do this again.
Yeah, definitely. We should
Right,
have more
and
time for discussion next time. Yeah.
right. And of course, always encourage communication and collaboration. So this is wonderful.
Mhm. Yes, and
All
everyone's
right.
welcome to join our meetings that happen at this time every 4 weeks, if you're ever interested.
Great. All right.
Right.
And I will share that with SMWLV as well.
Great.
Great. Well, thank you. And thanks to our speakers. This was a wonderful experience. So, okay.
Thanks.
Thank
Bye.
you.
Okay. All right.
Bye.